discussed about temperature indicator, and this is the circuit that we have used in the previous class to construct a temperature indicator. Now, in this class we will discuss about how to compute the various errors involved in this, because in analog circuit error computation is very important, because whatever we construct, that should give a accurate result. So, this class will concentrate more on error calculations, or we call generally in analog domain we call this error budgeting, because error budgeting has to be done. So, in this is the circuit that we have used in the previous class. Here actually we had used this LM335 as a temperature sensor, LM336 is a 2.5 volt reference zener. Since this LM335 gives at 0 degree C 2.73 volt, to compensate that 2.73 volt we have put this LM336 which is giving a 2.5 volt, and then we adjusted this resistance to make sure that at 0 degree C this is giving 2.73. At that time output comes 0, because this polarity and this polarity are opposite, this is minus, this is plus. So, this voltage actually subtracts that 2.73 volt which was coming there. So, net result is at 0 degree C it gives you 0 volt, 100 degree C it is giving you 1 volt. That is what we had seen in the last class, and then we also explained how to calibrate this using ice and boiling water, because you keep this one at ice and then adjust this P1 to get 0 degree C, and then keep this one at boiling water, adjust P2 to get 1 volt. So, this is to be repeated 3-4 times, P1 P2 adjustment to be done 3-4 times. That is, first to keep ice, adjust this, then keep it at boiling water, adjust P2, then again go to ice, adjust P1, again go to boiling water, adjust P2, like that 3-4 times. If you repeat, then you will get at 0 degree C 0 volt, at 100 degree C you will get 1 volt. This is what we had discussed in the previous class, and then we also said that what are the errors involved. Now, if we see this, this is a zener voltage, this LM336 gives you 2.5 volt fixed at all temperatures. It is supposed to give only 2.5 volt, and the voltage here should not vary with temperature, but LM336 zener voltage varies with temperature, that we had shown in the previous class. As if you look at the data sheet of LM335, that gives the LM336 is the zener, this temperature coefficient 30 ppm per degree C maximum, that is the rating that was given for this. So, if you calculate that, then we ended up in the previous class total drift zener voltage comes to be 7.5 volt. For example, if you see this total change for 2.5 volt for 100 degree temperature variation, 2.5 into 30 ppm into 100 degree C, that works out to be 7.5 millivolt change. That means the zener voltage changes by 7.5 millivolt when temperature change of 100 degree occurs. Now, if that means if I go back to the this circuit, if this changes by 7.5 millivolt, obviously this voltage also will change. Here, for example, this and this more or less gain of 1. If you want to know exactly, we have to find this divided by this resistance, that will give you exact gain. But if we see rough estimate, it is 1:1. So, here 7.5 millivolt change will produce nearly 7.5 millivolt change at the output. That means you will have when the temperature of this changes, or the temperature of the ambient temperature changes, because ambient temperature can change, as I said, for industrial grade equipment minus 20 degree to plus 80 degree. If taking as 100 degree change, you can expect 7.5 millivolt change here, but at this point 10 millivolt change is considered as a 1 degree C. That means because of the ambient temperature change, the zener voltage changes and the output voltage changes because of that, and you will have error of 0.75 degree, because 10 millivolt is 1 degree C, 7.5 millivolt end up in having 0.75 degree error. So, this xenon drift alone gives 0.75 degree C error at the output. So, this is first error. So, if you then if you look at the other errors, for example, this is the resistance that we are using, the resistance value also will change with temperature, this resistance also will change with temperature, this also will change with temperature. There is another error that we have to worry about it, because when these resistance change, the output voltage will change. So, even though the temperature of this is not changing, the output voltage will appear to be the output voltage will change, and that will appear to be a temperature change, and that is a significant error. One have to look into this. Then if you look in the operation amplifier by itself, the operation amplifier is having a offset voltage. That means that even when I give for example, I give here 0, then I expect output supposed to be 0, but you will not get 0, they will get some output voltage, and that voltage is coming because of the offset voltage, and the offset voltage normally represented with respect to the input. So, now if you see the look into the operation amplifier, I can show like this. If I take the operation amplifier and then draw this, we can show that it has an offset voltage, and then if I have a gain that depends on this RF and R1, then this is V offset. This is not the input voltage that I am applying, this is actually the offset voltage. This is there internally in the operation amplifier, and if you look at our discussion, the offset voltage is nothing but the voltage base emitter voltage difference between the two transistors, because now I redraw that operation amplifier circuit here, that if you look at the operation amplifier circuit, that you have the two transistors at the input, and that is connected to this. Recall our old circuit, plus 15 here and minus 15 here, and this is coming plus terminal, this is coming as a minus terminal. The base emitter difference between these two transistors, that you have base emitter voltage difference here, base emitter voltage, this is a base emitter voltage, this base emitter voltage difference, base emitter voltage minus this base emitter voltage, if both are equal, then offset voltage is 0, but there is small difference between the two base emitter voltages, this and this, that is actually coming as offset voltage. In fact, offset voltage itself is not a big problem, because when if the offset is there, you will get output voltage amplified by the gain and appearing at the output, but there is a provision in the operation amplifier to adjust the offset, that I can have if you see this one, there is, they call it offset voltage adjustment. One can adjust this and make it 0, but then that does not solve the problem, because that at one moment this offset voltage is continuously changes with the temperature, because if the temperature of the op amp changes, this VBE and this VBE, this VBE and this VBE will be changing. That means offset voltage changes with the temperature, that is this voltage changes with the ambient temperature. That means even if I adjust this at one temperature, another temperature this is not going to be get adjusted. That means it will definitely going to produce output voltage, because you cannot adjust each and every temperature this offset voltage. So, offset voltage adjustment only solves partly the problem. So, the actual issue is offset voltage drift. So, if I look at the data sheet, most of them give more importance to offset voltage drift than offset voltage. For example, if it is if you look at 741 data sheet says offset voltage drift as offset voltage drift as the offset voltage drift as plus or minus 15 microvolt per degree C, that is a V offset drift. They call it the V offset drift. So, the V offset drift of 741 is S plus or minus 15 microvolt. It means the change in voltage here at this point is 15 microvolt per degree C. That means if I take 100-degree temperature change for the ambient temperature, then the voltage change here supposed to be 15 microvolt into 100, that comes 1.5 millivolt. That means this voltage will the worst case it can be 1.5 millivolt for 100-degree. That means if I have a say 10 gain, then output will be 15 millivolt. Now the offset voltage drift is obviously a big problem, because for a given op amp, for 741, if I take, even if I take 100 pieces, each piece will have different amount. For example, one 741 from the same manufacturer can give you 0 offset voltage drift, another 741 can give you plus 15 microvolt, another 741 can give you minus 15 microvolt. That is why they call this is plus or minus 15 microvolt per degree C. So the exact value for a given op amp is not known. This is the biggest drawback in this. That is why we are struggling to compensate this offset voltage drift. There is no easy mechanism to solve this problem. Now that means while designing, we have to make sure the offset voltage produces very little error at the output. That is the approach that we have to take in the operation amplifier circuit design. So we have to select the required op amp such that the offset voltage drift contributes very little at the output. Now for example, in this case we have taken 15 microvolt. So if I want to amplify, in this case the offset voltage drift is 15 microvolt per degree C. So if I have a signal, for example if I want to amplify a thermocouple voltage signal, then for example I put this circuit and connect the thermocouple, I connect for example an operational amplifier is here, then I connect I give some gain, given gain, then I put the input voltage. Now you get V0 here. Now the gain I put RF R1. Now this is thermocouple voltage I want to amplify. Thermocouple gives me 40 microvolt per degree C. That is thermocouple, this is not a volt, this is a voltage source. Assume that I want to amplify say thermocouple voltage which is 40 microvolt, which is nothing but 1 degree temperature, or do not worry about temperature, assume this 40 microvolt to be amplified. Then by a factor of 10, then I supposed to get here 400 microvolt. After amplification V0 will become 400 microvolt. But then assume that this is at minus 20 degree, this op amp is at minus 20 degree C. Now if this goes to plus 180 degree C, which is which happens for the industrial grade equipments. Now if we take this 80 degree, then total temperature change, if you see this is 100 degree. Now for when, that means when 100 degree temperature change occurs in this op amp, and if this remains 40 microvolt, which is the voltage we want to amplify, when 100 degree temperature change occurs, we have to anticipate there is an offset voltage here, that offset voltage comes in series with this, we have to take it like that. This offset voltage can be now 1.5 millivolt, because if it is a 741, for 741 this becomes 1.5 millivolt, because the drift, as I said, is 15 microvolt per degree C. So for 100 degree C, that turns out to be 1.5 millivolt. That means automatically this 1.5 millivolt can appear depending upon that piece. One piece can be plus 1.5 millivolt, another piece can be minus 1.5 millivolt, another piece can be even 0, but none will be more than 1.5 millivolt. So in that case, worst case, now my output will be that will be this 400 microvolt. Say at this is, assume this is at this, for 80 degree, this would be 1 microvolt plus or minus this 1.5 amplified by 10 times, that is actually 15 millivolt. Now if you look at the output at 80 degree C, it will be 15 millivolt plus this 400 microvolt. Now you see that this is error, this is not the this 15 millivolt is error, and this is the signal. That means the signal makes no meaning at this point of time, that error is so large, and you will see that this amplifier is of no use, because the error is much more than the signal, and you will think 400 microvolt is corresponding to 1 degree C, because we know that 40 microvolt is 1 degree C. So, I amplified 10 times, I am expecting here 400 microvolt, then 400 microvolt is 1 degree C. Now, if you get for example 15 millivolt, then 15 millivolt corresponds to if you calculate in terms of temperature, 15 millivolt corresponds to 15 into 1000 microvolt divided by 400. That is this is I am converting 15 millivolt into microvolt by 1000, then 15 millivolt is corresponding to how much temperature, because 400 microvolt is 1 degree. So, I divide by 400, that comes 150 by 4. So, if you see this, so the error will be 15 into 1000 divided by 400, that comes 150 divided by 4, that is 37.5 degree C error. That means actual temperature is 1 degree, temperature is 1 degree C, but what is shown is 1 degree C plus or minus 37.5 degree. That means it may show in one case 38.5 degree, in another case it may show minus 36.5 degree C, because if one op amp can have plus offset voltage, another may give minus. If it is plus, it comes 1 plus 37, if it is a minus, 1 minus 37.5, that comes to 36.5. So, different op amps will give you different temperature from 38.5 to minus 36.5. It is a huge error. So, offset voltage drift is a significant problem in low level DC voltage amplification. So, one has to worry about this offset voltage drift as well. So, if I go back to our circuit, that is our temperature indicator that we were discussing, that errors involved. We had seen error due to this Zener drift, that was 7.5 millivolt drift, and that corresponding to almost 7.5 millivolt change here, that is 0.75 degree drift comes because of this. Now, this op amp also will have offset voltage, and the offset voltage will be drifting. The offset voltage drifting is the major problem. Even offset voltage is not a problem, that can be adjusted while calibrating this B1 and B2 adjustment, it can be taken care, it automatically taken care. So, offset voltage is not a problem in the circuit, but offset voltage drift is a problem. Now, in this case, if offset voltage drifts, then what will be the error that we will get? Now, if the offset voltage drifts, I have to put the corresponding offset voltage and see. So, I can put the offset voltage here. For example, if I had put here 1.5 millivolt here, because I am using 741 and that has a 15 microvolt drift. So, it is plus or minus 1.5 millivolt for 100 degree temperature change. If I put 1.5 millivolt, what will be the voltage that I will be getting? Now, to find that, I had to ground this and see how much times it is amplified at the output. Now, this is about 100K, this resistance is coming around 100K, and then you have here 100K. If I take this also nearly 100K, then if I ground this and this, then these two are coming, this resistance and this resistance coming in parallel, because I am grounding this and grounding this, and find out what will be the effect of this. That means 100K parallel 100K gives me around 47K. The 47K gives me gain of 1 plus RF by R1, that is around 3. So, you will have output voltage change of 4.5 millivolt. I will show the calculation separately here in the next page. So, let us see how will you now let us see the Now, if we see the effect of offset voltage drift, so I can show like this. Here this operational amplifier minus plus, and then we have this is around 100 k here, and then this is 1.5 millivolt here. This is come due to the offset voltage drift, and then you have one connected to this end, another connected to this end. This is nearly 100 k, this is nearly 100 k. In actual case, this is connected to our temperature sensor. This is connected temperature sensor that I grounded. This was connected to the Zener, the 2.5 millivolt. To find the effect due to this, I grounded this and this. Now I find what is the effect at the output. Now this will give me obviously the equivalent circuit of that. If I draw, that comes like this. If I put this, and I have 47 k and then 100 k, that gives me gain of 3. So, if 1.5 millivolt will give me 4.5 millivolt here. That means, offset voltage can give me 4.5 millivolt error at the output. Now, that is error, that means error due to offset voltage drift. V offset drift is equal to 4.5 millivolt. We had seen error earlier, error due to Zener drift, that was at the output equal 7.5 millivolt. So, we have this if we take this, this is correspond to 0.45 degree C error at the output, this correspond to 0.75 degree error, because 10 this is equal to 0.75 degree error. That means, you see now already we got error due to offset itself 0.45 degree, and error due to Zener is 0.75 degree at the output of the temperature indicator, which works out to be about 1.2 degree error total due to these two errors alone, the offset voltage drift and Zener drift. Because the drift is coming because the operational amplifier whichever we are using, that actually is sitting in the ambient temperature, and the ambient temperature is changing, because we should not assume the operational amplifier is always at room temperature, because room temperature is different at different place. As I said, if we are using in the industry, this unit might have been kept in the open air. For example, if it is a process control industry, all the equipments are put in the open air where sunlight falls directly on it. At the noon, you will see that temperature of the unit goes up to 80 degrees. So, if you are making for industry grade equipment, then you have to take temperature change as minus 20 degree to 80 degree. That is total change of 100 degree C, and only have to calculate offset voltage drift for 100 degree C. That is how we landed up at 1.5 millivolt. If I want to reduce this error, then I have to go for another op amp. For example, if instead of 741, if I take 714, then offset voltage drift is only 0.5 microvolt per degree C. Then 0.5 microvolt per 100 degree will give me 0.5 into 100 will give me about 50 microvolt change, and that will be very small, corresponding to 1.5 millivolt here, and correspondingly the output also will be only 50 millivolt into 10 will in this case 50 millivolt into 3 will give me only 150 or 50 microvolt into 3 will give me 150 microvolt, then automatically error comes down. So, if you want to reduce the offset voltage drift error, then we have to go for another op amp which is having a low offset voltage drift. That is why we have for different purpose different op amps. Some of them for DC applications we have to go for low drift op amp if the error what we are getting is considerable. If the error is not significant, one can use the same low cost op amp, because if you are looking for op amp of low drift, the cost enormously goes up, because for example 741 which is available for around 4 rupees automatically jumps to 50 rupees if I look for a 714 which is a low drift op amp. If I want still lower drift, you have to pay much more money. So, one has to see how much is the error, and accordingly we have to settle at the correct op amp without blowing up the cost of the equipment. So, this is a very important consideration. So, we have seen two errors if you go back our old circuit. our temperature indicator circuit, this circuit. Now, we have two errors, that is this error is due to offset voltage drift. Then we are seeing that temperature of this, when temperature of this changes and the voltage of the zener also changes little bit, that was 7.5 millivolt. So, totally this produces at the output of air 0.75 degree error, and this offset voltage produces 0.45 degree error at the output. Now, we have to see what are the other errors, because not these are not that these are the only two errors. There is another significant error is the resistances. Actually, the resistance values change with the temperature, and they change in a very peculiar manner. So, we see the resistance drift, how the resistance drift is occurring in a detailed manner. So, we will see, look into the resistance drift. Now, if you look at the circuit, for example, I take two resistance I put here, then I connect this, then I give the input here and connect this to ground. This is just inverting amplifier, and then we have a gain here RF and then R1. So, assume that I have put here 100k and then 10k, then the gain is actually 10. Now, if I give here for example 10 millivolt, then my V output V in is 10 millivolt, and then V output comes minus 100 millivolt, because it is amplified 10 times and inverted. So, I got minus 100 millivolt. The problem comes whether this 100 millivolt what we are getting here, is it constant or is it varying. Assume that this 10 millivolt input is constant, is not changing, and assume the op amp temperature also not changing, that means no parameters the op amp is changing. Even if we assume this, as long as this 10 millivolt constant, we expect this output supposed to sit at minus 100 millivolt, but this will not happen in the real life, because when the ambient temperature changes, resistance value of this is changing and the resistance value of this is changing. What is the gain that we have now is actually 10, that is because this is 100k, this is 10k, the ratio is 10. So, we got a gain of 10, but then when temperature goes up, then this resistance also will change, this also will change. And if you look at the temperature coefficient of these resistors, they will say the temperature coefficient of the resistance, look at the data sheet, they will give you temperature coefficient. For example, if the normal carbon resistance you take, they will say it is plus or minus 300 ppm per degree C. That means the resistance value can change by 300 ppm every 1 degree change. And note, the problem is it is plus or minus 300 ppm, not just 300 ppm. That is the one which actually complicates. What is happening is, if I buy 100 resistors from the same manufacturer, one resistance can go up, another resistance can come down. It can be same 100k, here 100k. Even then, one can go up, one can plus, when temperature increase, this may increase, this may decrease. However, in the other case, one may not at all change with temperature, other may change minus 700, or one may change plus 100 ppm, another may change minus 75 ppm, because it can be anywhere from minus 300 ppm to plus 300 ppm. Because normally we think that, for example, if I take a wire, that will have always a positive temperature coefficient, but when you make it a wire wound resistor, you will not get temperature coefficient as plus alone, because the characteristics of the entire resistor property changes when you make it as a pellet, or you make it as a wire wound resistor, you make it as a metal film resistor, then the property of the resistor is totally different from the pure metal property. So, one should not think that resistance will always increase only, or if I take all 100Ks, all 100Ks will increase, that is not true. So, even if you come buy from the same manufacturer, same batch, each resistor will behave differently as far as temperature with temperature change is concerned. One can increase, one can decrease, or one can change, no change at all, but none will change more than 300 ppm. that is the bottom line. So, if I take for example normal carbon composition resistance, they will say it is 300 ppm. That means assuming this is increasing by 300 ppm, this is decreasing by 300 ppm, that is the worst case that can happen. Then we see what is the error that we get because of the resistance change. Now we can calculate and see, for example, if I put 300 ppm, I will put the circuit. So, if I take this, so I assume this is plus temperature coefficient and this is minus temperature coefficient. Now, if this is 100 K, this is 10 K, we find out what is the change in resistance. So, delta R F, this is RF, this is R1 will be RF, that is 100 K. So, we take that is RF plus RF into temperature coefficient, which is 300 ppm, 300 divided by 10 power 6, that is 300 parts in 10 power 6 into temperature difference, which is 100. So, if I take RF as 100 K, that is 10 power 5, then this becomes 10 power 5 into 3 into 10 power 4. I combine these two and get 10 power 4 divided by 10 power 6. That comes out to be 100 K plus 10 power 5 into 3 into 10 power minus 2. That turns out to be 10 power 5 plus 3 into 10 power 3, that is 1000. That actually becomes 100 K plus 3 K. That means the resistance value of this had gone up by 3 K. There is 100 K become 103 K at plus 80. So, assuming that minus 20 degree it was 100 K, then at plus 80 degree this had become 103 K. Same way this 10 K we assume it is actually minus, if I calculate for this 10 K, then you will get the same equation. If I put delta, this is actually actual RF at 100 degree C, same thing I put Rn at 100 degree C, that will work out to be 10 power 4 plus 10 power 4 into 300 ppm. So, 300 in 10 power 6 into 100 degree C. So, that if you simplify, you will get 10 power 4 plus 10 power 4 into 3 in 10 power 4 divided by 10 power 6. That works out to be 10 K remains there, and then that actually 10 power minus 2 comes there. That if you go with this, then that becomes 10 power 2, that becomes 300 ohms. So, this actually we want to take this as minus temperature, negative temperature coefficient. So, eventually this actually becomes minus, actually if it is decreasing, then I should take it as minus. So, I remove this, I am taking this is decreasing with temperature. So, I am putting a minus sign. So, this is minus sign. So, eventually it now turns out at 100 degree C, RF had become 100 K plus 3 K and RI had become 10 K minus 300 ohms. Now, the gain is 103 divided by 10.3, not 103 divided by 10.3, which is not now if we see this gain, this is no, it's a 9.7, this is because 10 K, this is 9.7 K, this is another. So, now the gain is not 10, this now the new gain, if you calculate the new gain, because 100 K become 103 K, and 10K become 9.7K. That is the new gain, which is much more than 10. So, the actual calculation can be done, and then you get V output will be now 10 millivolt into this new gain, which will be close to around 11, and then you will get around 110 millivolt. So, originally he is supposed to get 100 millivolt, now you are getting 110 millivolt. This is a significant error because the resistance had changed so much. And if you want to reduce the resistance drift, one way is that you go for resistance which is having lower drift. For example, if I look at metal film resistors, you will get instead of 300 ppm various ranges. For example, we had shown the drift calculation, here we have taken drift as 300 ppm, that is why we have put 300. You have metal film resistor, 10 ppm is there, so 300 becomes 10, or you also have 50 ppm, you also have 100 ppm. So, you have the resistors of various values available, right from 10 ppm to 300 ppm, and of course, cost goes up. If you are looking for low drift resistance, then automatically the cost goes up. So, automatically when you look for low drift, then automatically cost goes up. So, one have to make a compromise, whether you need low drift resistor or not, that depends upon the application. So, this is the third error which we had seen, because in our temperature indicator example we had already shown two errors. One was due to Zener drift, which was 7.5 millivolt for 100 degree C. Another one is due to offset voltage drift, that was 4.5 millivolt at the output. And other one is this gain error, that we had calculated, we have not calculated, we had taken approximately 1 op amp, and then we had taken 10K and 100K because of the resistance change, how much is coming. Now, the same thing we have to go and calculate the error for our example circuit, that is temperature indicator circuit. What is the expected error? So, we go back to our we go back to this, we take this circuit and find out if this resistors and this resistor and this resistor changes, what is the expected error that you will get, because we can't assume that these resistors are not changing. In fact, resistor is an important part played in electronic circuit, where any circuit if we see, most of the parts will be actually resistors, and invariably they are ignored. But then even if you ignore, they will change against temperature and you will get an error. So, one should be very careful in dealing with the resistors. For example, if we had seen, if I had used 300 ppm resistor here and here and here, forget about the potentiometer values, assuming they are very small, the contribution can be for the simplicity we can neglect at this point of time. In actual case, we have to worry about that drift also. Invariably, many times potentiometers drift to more, because you do not get very low drift potentiometers, you will get up to 100 ppm only, whereas resistors you get up to 10 ppm. Now, for example, we take assuming that this also 100 ppm, we also got 100 ppm, that means total drift is 100 ppm, this is 100 ppm. Now, plus 100 ppm, 100 ppm, this is minus 100 ppm. If I take, what is the expected error at the output, assuming this is not at all drifting, that can give a worst case error. So, now we take this circuit and then we work out what is the expected error due to resistance drift in our temperature indicator circuit. Now, let me take that circuit redrawn here, so that it is easier. So, I combine the potentiometer and this, and the other side I had this connected to temperature sensor, that is connected here, that is minus 15, this is temperature sensor, this is 100K, and then I had this plus 15 and the Zener voltage, and then we had this and this. So, we assume that this is not drifting and this is drifting minus, and this is drifting plus. So, this value assume this both value put together is 100K. So, if I calculate this, what is the resistance it will become, that actually become 100 ppm if I take, then it will be 100K plus this 100K is 10 power 5 into 100 ppm, 100 by 10 power 6, for 100 degree I put this. So, that actually becomes 10 power 5 plus 10 power minus, this is actually 10 power 9. So, that become 10 power 3, 4 plus 5 9 goes with 3. So, it becomes 10 power, that means that this resistance become 101K. So, this will down by 101K. So, this actually becomes 99K, this actually becomes 101K. So, gain error will be the, so this voltage only amplified here and put out. So, if I assume that 100 degree C, this is sitting at 3.73, because this will be sitting at 3.73. So, we had find out what is the change that comes when these two are 100K, and when this is 101 and 99K, what is the change that you expect. So, when gain is equal to 1, when gain is equal to 100K by 100K, because both are 100K, then the gain is actually 1, the contribution output contribution V out due to sensor, that becomes 3.73, because the gain is 1. So, that when gain is equal to at high temperature, then the gain actually become 101 divided by 99, then V0 becomes, then V0 actually becomes 3.73 into 101 divided by 99. So, that actually definitely goes more than 3.73. We can calculate this. So, you will get roughly about 10 millivolt error is expected. It will go to 3.831% error, that will be nearly 37.3 millivolt error is expected. You calculate and see what is the difference, because we have to calculate this minus 3.73 if I put, that is the error will be 3.73 into 101 divided by 99 minus 3.73, which may come around 37 millivolt, maybe nearly equal to 37 millivolt. You calculate exactly, I am not doing the calculations here. Now, this is actually corresponding to 3.7 degree error, which is quite large. That means resistance drift produces a large error at the output. So, if we look at our circuit now, we have calculated 3 errors so far. One is Zener drift error, which was 7.5 millivolt, which correspond to 0.75 degree at the output. Then we had resistance drift here, that is equal to 37 millivolt, that is equal to 3.7 degree error. And similarly, we have calculated offset voltage drift of op amp, that was 4.5 millivolt, and that was coming 0.45 degree error. You see, total error goes now already 5 degree. That means, if my temperature indicator instead of showing 100, it can very well show more than 100 actually, either 105 or 95. Now, this is a significant error. If I want to reduce, then I should go for Zener, which is having low drift, and that costs extra money. For example, we have a Zener up to 1 ppm. This is actually 30 ppm, which gave me this. I can go to 1 ppm, then that automatic error comes down. Or resistance drift, this is per 100 ppm resistor, this is 37 millivolt. If I go for 10 ppm, then the error will come down, but of course the cost more money. then I can go for much better op amp. So, instead of getting 4.5 millivolt error, I will get much lower error, then this also comes down. Of course, again you have to pay higher cost for that. So, of course, now I think you understood why component selection is very important in analog circuit, because if you select proper components, then error will be less. Otherwise, the circuit may work now, but it will show enormous error when the ambient temperature changes, and this is a very important aspect in analog circuit design, because the error budget is a forgotten story in analog domain, because no one bothers that the one have to think the assumption that many of them make is that you connect to op amp and that amplifies and puts it at the output, no need to worry about anything. That is totally wrong. One had to worry about various errors associated in the circuit. In fact, we have seen only 3 errors in the circuit so far. There are many more errors in this which we are not discussing at this point of time, because I do not want to add in one stroke all the errors. We will see in another circuit other errors involved. For example, in this circuit there are other significant errors. For example, if I take the this circuit which in this case, for example, you have a bias current to the op amp, that current goes through this, the bias current also changes with temperature, the bias current produces error, that we have to calculate that also. I am not doing it here because I do not want to burden you at this point itself with all the errors. There are many more errors in the op amp itself. So, we will see them one after another. So, in this example we will stop with these 3 errors. Now, by now you would have understood that in analog circuit design the component plays a significant role, particularly for example, if you take resistors, if you take any, for that matter, if you take any analog circuit, you will find plenty of resistors and capacitors, and one should not take that only the value is important, the drift of these resistors and the drift of these capacitors are not important. One should not take that view. They are very, very important and one should consider them. So, at this point it is appropriate to discuss little bit about what are the types of resistors that is available, and what are their characteristics and which one to use where, and similarly what are the different capacitors available, and then what are the important characteristics and which one to use where. That should be discussed at this point of time before we build up very many circuits using these resistors and capacitors. So, I will spend another few minutes in explaining what are the different resistors and what way their characteristics affect the circuit. For example, if we take resistors, you get in the market mainly three different type of resistors. That is, one is carbon composition, then you have the second type coming as metal film resistors, and then third type coming as wire wound resistors. Now, if you look at the carbon composite resistors, that temperature coefficient is very high, you get plus or minus 300 ppm is per degree C, that is the temperature coefficient that you get. Now, if you look at the metal film resistors, you get 10 ppm per degree C to 100 ppm per degree C, that is the thing you get. Wire wound resistors, that you get manganene at the lowest side, you will get again 10 ppm per degree C. These are plus or minus. Manganene means only plus, not minus, 10 ppm per degree C. The wire wound resistors always temperature will increase with temperature, no question of minus actually. And the other extreme end, if you go for copper wire or platinum wire, that you will get copper wire, then that resistance changes by 3000 ppm per degree C. That means the wire wound resistors, not all wires have the same temperature coefficient, but nevertheless one good thing about wire wound resistor is all of them will only increase with temperature, they will not decrease, unlike these metal film resistors and carbon composition resistors, they can increase, decrease, and we do not know how much actual values. It is only maximum value is plus or minus 300 ppm. So, one in one lot, even metal film resistors, if you buy, one resistance can go up, another resistance may come down, one may not drift at all, one may be drifting 10 ppm, another may be drifting 8 ppm. What this means, for example, if you ask metal film resistors, ask them to supply 10 ppm temperature coefficient resistors, you will give me 10 ppm resistors, but it does not mean all of them are drifting 10 ppm. None will drift more than 10 ppm, one may drift 8 ppm, another may drift minus 6 ppm, another may drift 0, but none will drift more than 10 ppm plus or minus. Similarly, I can ask metal film resistor 25 ppm available, 50 ppm available, 100 ppm available. So, we have to specify, if we are buying a metal film resistor, what is the temperature coefficient that we are looking for. It is a 10 or 25 or 50 or 100 ppm, that we have to specify. All carbon composite resistors will come only with 300 ppm, that you need not specify. Automatically, if it is a carbon composition, then you will get only 300 ppm. Even in metal film also, we have two different types that almost nowadays they are forgotten. So, need not worry at this point, but wire wound resistors, normally what you get all will be about 3000 ppm. Manganese is the only wire which gives you very low temperature coefficient of 10 ppm, that is very expensive. Unless you need for a special purpose where low drift is called for, you should not go for this. So, otherwise if you do not specifically ask, they will give you 3000 ppm to 4000 ppm resistance only. So, wire wound resistance having very high drift. Now, in addition to the drift consideration, we have to worry one more thing about resistor is the resistor value not only changes with temperature. Suppose if I take one carbon composition resistor, which is actually say 10K, which is 10K and 300 ppm. Now, I assume it 10K at 25 degree C. Now, after 1 year use, if the same 10K, if I see at the same room temperature 25 degree C, it is not going to be same 10K. With the age, the resistance value changes, and that is very high for carbon composition resistance, that is very little for metal film resistors, because metal film resistors exhibit very low aging property. With the age, resistance change is very little for metal film resistors. They invariably tell in terms of percentage, per year how much it will change, 0.1%, whereas this changes up to 1%. But wire wound resistor, the change mainly due to how oxidation takes place. If it is properly sealed, then wire wound resistors aging problem is very little. So, for long time use, then wire wound resistor is good, but they have a large temperature coefficient. This is actually good because it is very cheap, that is all, but then the drift is very high. This is good for low drift, but then the cost is high. For example, if you take normal quarter watt resistor, you will get it for 25 paisa a year, whereas this you have to spend about rupee a year, and this depends upon the wattage of the resistor. So, in addition to tolerance of the resistance and the wattage, what is the wattage of the resistor, there is one more property that we have to realize in analog circuit use, that is this temperature coefficient and then the long term drift. So, if you want a very low temperature coefficient, then you go for metal film resistor, and if it is not necessary to be low temperature coefficient, then it is enough if you go for carbon resistance, because do not try to put everywhere metal film resistors, then your equipment will not be sellable, because the cost will enormously go up. So, one need to apply their mind and see which resistor to be used which purpose. Now, similarly that if you look at the capacitors, we have three different types of capacitors available. Now, if we look at the capacitors, we have one type as ceramic capacitors, and the second type as electrolytic capacitors, and then third type yes, plastic film capacitors. Now, if you look at these characteristics and their usage, they are totally different. Like resistors, we also have to be very careful about capacitors usage and their properties, because in analog circuit design that is a major issue. Now, ceramic capacitors, for example, you have ceramic used as a dielectric, and these capacitors available maximum of 10 microfarad value only. Now, if you look at electrolytic capacitors, where there are two types of electrolytic capacitor. One is aluminum electrolytic, or aluminum oxide used as a dielectric, and then another one is tantalum oxide. Tantalum oxide is used as a dielectric, and they will come as electrolytic capacitor. This is available in large volume. You will get in even today in few farads, right from 10 microfarad to few farads capacitor available, large value, whereas ceramic capacitor available only up to 10 microfarad, not more than that. Now, in plastic film, various plastics, for example, polycarbonate, polypropylene, various plastics are used as a dielectrics. Now, if we see their properties, the ceramics have very high, the ceramic is used as a dielectric. The dielectrics of these capacitors have very large drift due to temperature. For example, the dielectric constant of this capacitor will change, because dielectric constant only determines the capacitor value. So, when dielectric constant of this capacitor change, then the capacitor value also changes. So, ceramic capacitors have a large temperature coefficient. Electrolytic capacitors also have a large temperature coefficient. Plastic film capacitors have very low temperature coefficient. So, also there are various other properties which we will see in the next class, but we have to worry about these properties also, and we correctly select them for proper use of these capacitors. So, we had shown in this class what are the errors that is coming in the temperature indicators circuit. We had shown 3 errors, that is, one is drift due to the Zener, other one is offset voltage drift error, and third one is resistance drift error. These 3 errors put together, how much was the total error that we had shown, and I also shown you how to reduce them. And also we have discussed about various resistors that is there and their characteristics, and we have discussed little about these capacitors. We will continue our discussion in the next class. Thank you.